Steel gives us the power to build big and build strong. Its strength-to-weight ratio is just phenomenal. This means we can create structures that are both incredibly tough and surprisingly light. From the delicate instruments a surgeon uses to the massive gears in a wind turbine, steel provides the backbone. It's the material that allows our most ambitious engineering dreams to take shape, turning blueprints into towering realities and sketches into powerful engines. The magic, though, isn't just in its strength, it's in its adaptability. By adding a pinch of this element or a dash of that one, a bit of chromium here, a touch of nickel there, we can change its properties completely. We can make it shiny and rust-proof for our kitchen sinks. We can make it hard enough to cut other metals for our workshop tools. We can even make it flexible enough to act as a spring in your car's suspension. This is why there isn't just one steel. There are thousands of recipes, each one cooked up for a specific job, giving engineers a massive toolbox of materials to choose from. Let's go on a world tour of steel codes. It's less complicated than it sounds, honestly. I believe you have definitely heard about ASTM standard. ASTM, or the American Society for Testing and Materials, is a global organization founded in 1898 that creates technical standards to ensure materials and products are safe and reliable. These standards are used across many industries and cover materials like metals, plastics, and textiles. The ASTM Steel Grade Designation System is a structured way to identify and classify steel materials based on their properties and intended applications. It typically starts with a prefix, like A for ferrous metals such as steel and iron, followed by a number that represents a specific standard specification. This number refers to a detailed document that outlines the steel's chemical composition, mechanical properties, and testing methods. Some grades also include a suffix, such as grade 70, which indicates a variation within the standard, often based on strength or toughness. Additional letters may be added to specify product form, processing method, or metric units. For example, ASTM, a 516 grade 70 refers to a pressure vessel steel with a minimum tensile strength of 70 ksi. This system helps engineers and manufacturers ensure they are using the right material for performance, safety, and compliance in various applications. Now let's look into AIC and SAE standards. SAE International, formerly known as the Society of Automotive Engineers, is a global standards organization based in USA. It changed its name in 2006 to reflect its broader focus beyond just automotive engineering. Today, SAE develops technical standards for a wide range of industries including aerospace, commercial vehicles, and emerging technologies like autonomous systems. Its work supports the design, testing, and safety of vehicles such as self-driving cars, trucks, drones, and other transport systems, helping engineers ensure performance, reliability, and compliance across the industry. The SAE Steel Grade System is a standardized way to classify steel alloys, managed by SAE International. It was developed in the 1930s and 1940s in partnership with the AIC, or the American Iron and Steel Institute, to create a unified numbering system for steel types. While both the SAE and AIC systems are used to classify steel grades, the SAE system is more detailed and widely adopted today. The SAE system has continued to evolve while AIC has stopped publishing material specifications. As a result, SAE designations are now the standard reference in most industries, while AIC designations are still commonly referenced, particularly for stainless steels, but are no longer actively updated. The SAE system provides more comprehensive information about the steel's chemical composition and mechanical properties, making it especially useful for engineers and manufacturers when selecting materials for specific applications. AIC was founded in 1855 and provides a classification system based on the chemical composition and mechanical properties of carbon and stainless steels. For example, AIC 304 is a stainless steel known for its corrosion resistance, commonly used in kitchen and food processing equipment, while AIC 1018 is a low-carbon steel valued for its good weldability and machinability, often used in general fabrication and manufacturing. Now let's break down the AIC designations. Take AIC 1045, a popular carbon steel. The first digit, 1, tells us it's a basic carbon steel. The second digit, 0, means there are no major alloying elements. And the last two digits, 45, tell you the carbon content in hundredths of a percent. So, 1045 has about 0.45% carbon. It can be SAE 1045 or AISE 1045. Simple, right? This steel is tough and strong, so you'll find it in things like gears, axles, and crankshafts. Now let's jet over to Europe, where they use the EN standards. European standards, abbreviated as N from the German term Europäische Norm, are technical standards developed and maintained by three main organizations: CN, European Committee for Standardization, CENELEC, European Committee for Electrotechnical Standardization, and ETSI, European Telecommunications Standards Institute. These standards are designed to harmonize technical specifications across European countries, ensuring consistency, safety, and interoperability in products, services, and systems. In the context of steel and materials engineering, EN standards define grades, testing methods, and performance requirements for various types of steel, including structural, stainless, and tool steels. They are widely used across the EU and often align with international standards to support global trade and engineering practices. The EN 10000109999 series of European standards focuses specifically on iron and steel. EN 10025 is a key standard for hot-rolled structural steel products, divided into multiple parts that define delivery conditions for different types of structural steels, including non-alloy, fine grain, and corrosion-resistant grades. EN 10088 focuses on stainless steels, listing grades and specifying delivery conditions for various forms like sheets, plates, bars, and wires. Other important standards include EN 10204, which defines types of inspection documents for metallic products, and EN 10216 and EN 10217, which cover seamless and welded steel tubes for pressure purposes, with specifications for different temperature and alloy conditions. EN 10305 addresses precision steel tubes used in hydraulic and pneumatic systems, while EN 10270 defines steel wire for mechanical springs. EN codes are a bit more descriptive. A great example is S275JR. The S stands for structural steel. The 275 is the minimum yield strength in megapascals, which is a measure of how much stress it can take before it starts to permanently deform. And the JR part tells us about its toughness. In this case, it has been tested to withstand a certain impact energy at room temperature. You'll see S275JR everywhere in construction, forming the beams and columns of buildings and bridges across the continent. Next stop, Japan and the JIS, or Japanese Industrial Standards. Their system is also quite logical. Let's look at SS400. The SS stands for Steel for General Structure, and the 400 represents the minimum tensile strength in megapascals. Tensile strength is the maximum stress it can handle before it snaps. Like its European cousin S275, SS400 is a workhorse in the construction industry. It's used for plates, bars, and sections in buildings, bridges, and ships. It's a reliable, all-purpose steel that gets the job done without any fuss. Finally, we land in India, where the Bureau of Indian Standards, or IS, sets the rules. A common structural steel here is IS 2062 E250. The IS 2062 is the standard number that defines the requirements for this type of steel. The E stands for engineering steel, and the 250 is the minimum yield strength in megapascals, just like the European system. This steel is the backbone of much of India's infrastructure, used extensively in everything from railway tracks and industrial sheds to transmission line towers. It's a testament to how different codes can all point to steels that perform very similar vital jobs around the world. So, we know there are thousands of steels, but they can be sorted into a few big families. First up, we have the carbon steels. These are the most common and are basically just iron and carbon. They are split into low, medium, and high carbon. Low carbon steel, like AIC 1018, is soft and easily shaped, perfect for car bodies and sheet metal. Medium carbon steel, like our friend IEC 1045, is stronger and harder, used for gears and machinery parts. High carbon steel is very hard and holds an edge well, which is why it's used for cutting tools and springs. It's all about the carbon content. The more you add, the harder it gets. Next, we have the alloy steels. This is where we start getting fancy. Alloy steels are carbon steels with other elements deliberately added to change their properties. Adding chromium makes steel harder and tougher. Adding nickel increases its strength and resistance to impact, even at low temperatures. A classic example is 4140 steel, which contains chromium and molybdenum. This combination makes it incredibly strong and wear-resistant, perfect for high-stress applications like drill collars in the oil and gas industry or bicycle frames for serious cyclists. These are the designer steels, tailored for tough jobs. Then comes the shiny one, stainless steel. Everyone knows this from their kitchen. The secret ingredient here is chromium, and lots of it, at least 10.5%. The chromium creates a thin, invisible layer on the surface that protects the iron from rusting. It's like giving the steel a permanent self-healing raincoat. A common type is 304 stainless steel, which also contains nickel for added formability and corrosion resistance. This is why it's perfect for kitchen sinks, cutlery, food processing equipment, and even surgical instruments, where cleanliness and rust prevention are absolutely critical. Finally, we have the super specialists, tool steels and special steels. Tool steels are the hard nuts of the steel world. They are loaded with elements like tungsten and vanadium, making them exceptionally hard, wear-resistant, and able to hold a sharp edge even when red hot. An example is D2 tool steel, used to make dies that stamp and cut other metals. Special steels are a broad category for materials with unique properties like electrical steels used in transformers or weather-resistant steels like Corten, that form a stable, rust-like appearance to protect themselves, often used in outdoor sculptures and architectural facades. So, you're an engineer with a brilliant idea. How do you pick the right steel from this enormous catalog? It's a massive balancing act, a series of trade-offs where you have to be a bit of a detective and a bit of a fortune teller. The first and most obvious factor is strength. The steel must be strong enough to handle the loads it will face without bending or breaking. A beam in a bridge needs immense yield strength to support the weight of traffic, while the steel in a paper clip just needs to be strong enough to, well, hold paper. But making steel stronger often makes it more brittle. This leads us to the next critical trade-off: toughness versus hardness. Think of the difference between a ceramic plate and a rubber mallet. The plate is very hard but shatters easily. It's brittle. The mallet isn't as hard, but it can take a beating. It's tough. Engineers often need a steel that finds a happy medium. For a chisel, you want it to be hard enough to hold an edge, but tough enough not to shatter when you hit it with a hammer. This balance is often controlled by the carbon content and by heat treatment processes like quenching and tempering, which are like a spa day for steel to get its properties just right. Another huge consideration is the environment. Is the steel going to be sitting in a dry office or getting splashed by seawater on an oil rig? This is where corrosion resistance comes in. For a salty or chemical-heavy environment, you'd be mad not to choose stainless steel or apply a protective coating, even though it costs more. For a simple indoor bracket, a basic carbon steel will do just fine. Ignoring corrosion is asking for trouble, as rust can slowly eat away at a structure's strength, leading to failure. It's a slow-motion disaster that good engineering can prevent. And finally, the factor that no engineer can ever ignore: cost. A super strong, ultra-tough, corrosion-proof wonder steel might be perfect for the job, but if it costs a fortune, your project will never get built. Engineers must always weigh performance against price. Sometimes a cheaper, lower-grade steel with a clever design or a protective paint job is a much smarter solution than an expensive alloy. The goal is to find the most economical material that meets all the safety and performance requirements for the entire life of the product. It's this constant juggling of strength, toughness, longevity, and cost that makes steel selection one of the most crucial decisions in all of engineering.